So guys, welcome back to my YouTube channel. I'm still on the series STA Design and Analysis of Experiments, and now we're moving on with the complete analysis of variance of the CRD model. This is the CRD model. In our last videos, we've been able to learn how to estimate the parameters or the components of the CRD model. We're able to derive an equation for the overall mean of the CRD model, which its symbol is mu. We're able to derive an equation for tau I, which stands for the height treatment effect of the CRD model. And also, we further learned how to partition the sum of squares of the CRD model, which led us to deriving our TRSS, which stands for the treatment sum of squares, and deriving our TSS, which stands for the total sum of squares. Now today we're going to be looking into the one-way ANOVA table. This is the technique that is used in the complete analysis of a completely randomized design. The CRD stands for the Completely Randomized Design. So one-way ANOVA table is the method of analysis that is used to do a complete analysis of the CRD. So this is the one-way ANOVA table layout, and this column contains the sum of variations. There are the treatment, the random error, and the total under the first column. Then the second column contains the degree of freedom. We have the k-1 degree of freedom, kn-k degree of freedom, and the sum of this will give us a total of kn-1 degree of freedom. And the third column contains the sum of squares, and the first one is the treatment sum of square, the second one is the sum of squared error, the third one is the total sum of squares, and the next column is the mean square. The first one is the mean square of the treatment effects, and this is derived by dividing TRSS by the first degree of freedom, k-1. The next one is the mean squared error, which is derived by dividing SSE by kn-k, which is the second degree of freedom. And so finally, the last column, which is the most important part of the ANOVA table, is the test statistic, which is the F ratio. This F ratio it is a test statistic that we use in our hypothesis testing for the analysis of a completely randomized design. And so the test statistic, or the F ratio, which is the F ratio rather, is gotten by dividing MSTR by MSE. So that is how we get the F ratio. Now, moving on to the hypothesis. We have the null hypothesis and the alternative hypothesis. And for a completely randomized design, the null hypothesis always say that there is no significant difference among all the treatment's main effects. That is the tau 1, the tau 2, the tau 3, up to the tau k, which stands for each treatment. So, and the H1 always say that for at least one treatment, there is a significant difference among the treatment's main effects. So, and the decision rule goes thus: we reject H naught, which is a null hypothesis, if the test statistic, remember our test statistics is our F ratio, which is derived by dividing MSTR, which is the mean square of the treatment, over by the mean squared error, MSE. So we reject the null hypothesis if this test statistic derived here is greater than the critical value. The critical value is also known as a tabulated or the table value that we're going to get from our Fisher distribution table. Otherwise, we do not reject. Now let's look at this practical question. It says an engineer is interested in how the mean absorption of moisture in concrete varies among 4 different concrete aggregates. 5 samples of a concrete were exposed to moisture for 48 hours. The following results were obtained. So this is the results. This is the data that was given, that was recorded from the experiments that was carried out by the engineer. Each treatment in this case stands for the moisture absorption of each concrete that was exposed to moisture. So we have treatment A, we have treatment B, we have treatment C, and treatment D. So these are the questions. The first question says state the null and alternative hypothesis for this experiment. The second question, construct a one-way ANOVA table for the data above. The third question, test for significance of the aggregate as 5% level of significance. The fourth one states the conclusion in context of the problem. And the fifth question, estimate the components of the suitable model for this design. So let's go through for the solution. So the first question says, state the null and alternative hypothesis for the experiment. And so the null hypothesis goes to us: the mean moisture absorption is equal across all concrete aggregates. If you remember, we said the null hypothesis always says that the treatments are equal, the treatment effects are equal, and the alternative hypothesis says otherwise, that the treatment effects are not equal for at least one treatment. So the alternative hypothesis therefore says there is a significant difference among the mean moisture absorption. Here now, like I said earlier, that the treatment that is being considered here is the mean moisture absorption of the concrete aggregates. The mean moisture absorption is the treatment effect that is being considered here. So there is a significant difference, as the alternative hypothesis now, among the mean moisture absorption of the concrete aggregate for at least one aggregate. So that's the answer to the solution to the first question that is required. Now, moving on to the second question that is required. The second question says that we should construct a complete ANOVA table, a one-way ANOVA table for that experiment. And in order to be able to get our one-way ANOVA table, we're going to be needing the degrees of freedom, we're going to be needing the sum of squares, we're going to be needing the mean squares. In order to get the mean square, we get the sum of squares. And this is the sum of squares, as we have partitioned it here, is that we have SSE, which is the sum of square error, to be TSS, total sum of squares, minus TRSS, treatment sum of squares. So, in order to get our ANOVA table, we are going to be needing this. And in order to get this, like we have learned in our last video, that the formula for TSS is summation y ij, I equals 1 to k, j equals 1 to n squared minus y dot squared over p. So this is the treatment sum of squares is summation of I equals 1 to k of y I dot squared over n minus y dot square over k n. So let's go through the step of calculating this one by one. So we are going to be needing our y dot, which is the sum of all observations under all the treatments. So we can use this yi dot to derive our y dot, because the sum of all the yi dots that we get under each treatment will result to y dot. So we are going to be summing the values here, the values here, the values here, the values here to get each the sum of each treatment, the sum of the observations under each treatment. Plus, so if we sum this plus this plus this plus this plus this, we are going to get 26.86. And the sum of all these is going to yield 30.54. The sum of all these likewise is 29.65. The sum of all the values here is 28.71. So this stands for the sum of all observations under each treatment. The sum of all observations under each treatment. In order to get our y dot, it is equals to the sum of all these all together. And so our y dot is 115.76. So moving on from there, let's calculate our TSS first. So for the TSS, this is the formula we are using. And let's start by finding this part first. So we have summation yij squared, I equals 1 to k, j equals 1 to n. So this summation yij squared simply means that you square each observation on the data layout before you sum all the results together. Remember, yij stands for the jth observation under ith treatment. And if you take a look at the data that we have, you realize that there are 4 treatments and there are 5 observations under each treatment. So the observations under all these treatments, you are going to square them one by one and sum everything together. So this is going to give us 4.53 square plus 5.71 square. Then finally, after summing everything together, the result we are going to get is 677.93. And so we do the other parts of the formula, which is usually called the correctional factor. That is y dot squared over kn, which is equals to, now from our table we can see that y dot, which is the sum of all yi dots, is 11.76. So we just apply that. We have 11.5.76 squared over, now our k is the number of treatments that we have. There are 4 treatments in the data that was given, and n is the number of observations per treatment, and there are 5 observations per treatment that was given in the data. So if we apply that to this, we have over 4 times 5, which gives us 1340.37 divided by 20, which is equals to 670.018. So our TSS, which is summation yij squared minus y dot squared over kn, is now going to be 677.93 minus 670.018. So therefore, our TSS is going to be 7.9. So the next thing is to calculate our TRSS. And the formula for TRSS is given as this. So we take the first part of the formula, summation yi dot squared over n. And from this table, we can see that we've been able to calculate each of our yi dots. So yi dots represent the sum of all the observations under each treatment. And what this formula is simply saying is that we square each of these yi dots, then we sum all of them together, then divide by n. So from here, we square 26.86, add it to the square of 30.54, and so that is what we have here, up to the square of 28.71, all divided by 5. And so what that is going to give us is 33557.53 divided by 5, which will give us 671.506. And so the next thing is to calculate the remaining part of that formula, which is y dot dot square over kn. It's the same as we've calculated under total sum of square. It is a correctional factor, so it is always the same. So we have 11.576 squared over 20, which will give us 670.018. So the next thing is to now apply these values to our formula. So therefore, our TRSS is equals to 671.506 minus 670.018. Therefore, our TRSS is equals to 1.488. Now, we apply these two values back to our sum of squared error. The sum of squared error is the difference between the two of them. So we have SSE equals the difference between TSS and TRSS. So what's our TSS? So our TSS is 7.912 and our TRSS is 1.488. So if we subtract these two, we are going to get our SSE to be 6.424. So from there, we move on to drawing out our ANOVA table. So this is a theoretical ANOVA table where we have the treatment, random error, the total, the degree of freedom. So what it simply does is that it gives us a guide as to how we are going to be constructing our practical ANOVA table. So the second question, now this is the final answer to the second question in the practical question, that we should construct a complete ANOVA table for the data. And so this is the column for our degree of freedom. Now, you need to take note of this, that the treatment in this case now is moisture absorption. I've mentioned that several times in the analysis, during the analysis. So the treatment is no longer treatment here, because this treatment is just a theoretical terminology that is general. So, and in this case, in the case of the question that we are solving, the practical that we are dealing with, the treatment that was applied to the experimental materials was moisture absorption. So now, the next thing is to get our degrees of freedom. And so the K is the number of treatments. And from the question or from the data that was given, there were 4 treatments. So our K is going to be 4 minus 1. That gives us 3. And so the second one, which is the Kn minus K under the random error, is going to be 4. It's 5. N is the number of observations under each treatment. So we have 4 times 5 minus 4, which gives us 20 minus 4. That's 16. And the last one, which is Kn minus 1, that's 4 into bracket 5 minus 1. And that's 4 times 5, 20 minus 1, that is 19. So for the sum of squares, the first one, which is the TRSS, as we have solved and calculated earlier, is 1.488, followed by the SSE, the sum of squared error, which was calculated to be 6.424, and lastly, the total sum of squares, which was calculated to be 7.912. So the mean square is simply this treatment sum of square. Now for the first mean square, which is the mean square of the treatment, is going to be treatment sum of square divided by this degree of freedom. So when we do this divided by 3, we are definitely going to be having 0.496. And when we do this divided by 16, we are going to be having 0.402. And so our F ratio finally becomes this over this, which is MSTR, this over MSE, this. So we have 1.235. That is our F ratio. And remember that our F ratio is a test statistic. So we've answered the second question. Now, moving on, let's go to the third question. So the third question says that we should test for the significance of the aggregate at 5% level of significance. So we've been given 5% level of significance to test for the significance of the aggregate. So that says that the first thing now is to calculate our table value or our critical value. And so the critical value the first step to that is in writing, stating our alpha. Our alpha is the level of significance, and alpha here is 5%, which is equals to, which is equivalent to 0.05. So, followed by the degrees of freedom. So, after we've gotten our level of significance, the next thing is to get our degrees of freedom. And so, for our degree of freedom, this is F distribution, which usually have 2 degrees of freedom. So, we have this K minus 1 and Kn minus K. So, K minus 1 is 4 minus 3, 4 minus 1, which gives 3, and Kn minus K is 4 into 5 minus 4, which gives 16. So our critical value or tabulated value is going to be this f of 0.05, 3, 16. And if we look this up on the f distribution table, it's going to be 3.24. So the next thing is to get our test statistic, and that's not hard at all. We've already derived our test statistic using the ANOVA table. And like I said earlier at the beginning of this particular tutorial, that's the one of the major aim of the ANOVA table is to be able to derive our test statistic for the purpose of hypothesis testing. So the test statistic here is MSTR over MSE, and for our own analysis, which was calculated to be 1.2635. So our F ratio, which is the test statistic, is 1.235. So now we move on to our decision rule. So remember, our decision rule states that we reject the null hypothesis if the test statistic is greater than the critical value. Otherwise, do not reject. So our decision is this: since F ratio, which is equals to 1.235, is lesser than the F tabulated, that is the critical value, which is equals to 3.24, then we do not reject page notes. That is our decision, and that actually answers the question that was asked in number 3.